So before we get started, the makeup interview and quiz grades have been posted at Autolab. If you took the makeup, not makeup, but second chance quiz or interview last week, you should have your results in Autolab. If you didn't pass both the quiz and interview, you should have received an email from Ruslana explaining what the procedure is for making those up, what the next round looks like. So hopefully there are no questions about that, but if there are, let me know, contact us, reach out. And talked about it. Hey, Cole. Dragos apparently doesn't want to say hi today, but hi, Cole. Oh, never mind. Yeah, slacker Dragos. All right, anyone have questions or anything, or any open issues before we get into lecture content? Yes. If you get an extension on a project for the right portion, you can't complete any of the application objectives, right? Correct. Okay. Yeah. So if you get an extension, you can't complete the application objectives during that extension. But if you completed an application objective before the extension, you'll still get credit for that. Autolab will show a 0 afterwards, but you will retroactively get that. Like I'll go in and correct that at the end of the semester when I do grades. Okay. Anything else? All right, let's talk about merge sort and start talking about recursion. Drink poison last night. Yeah, that happens. Sup, Dragos. So lecture task 2. The lecture tasks for this learning objective, I'll say up front, are a little bit disjoint with the lectures. I just couldn't get the lecture tasks to line up with lectures as neatly as I like to. For this learning objective. So this doesn't have much to do with merge sort and recursion, but you could do this lecture task with Wednesday's lecture content, with Mondays and Wednesdays. So I just needed to attach it to a lecture somewhere, and I didn't want to put 2 lecture tasks in one lecture on Wednesday. It's so just know if you're trying to apply today's lecture content to this lecture objective, or this lecture task, you don't need today's lecture content until lecture task 3. 3 and 4 will be our recursive lecture tasks. So just a heads up on that. This one follows the same procedure, the same structure as lecture task 1, as your average and top K. Same thing, we're going to take a method. We're going to take a function, sorry, not a method. We'll write a method that takes a function that takes a t and returns a double, and a list of t with the type parameter t, except now we're computing the standard deviation. So just like one next step from lecture task 1 is just a little bit more complex math. Standard deviation instead of average top k. And it gets a little bit trickier, not too much, but a few of the shortcuts that students like to take, which is there's nothing wrong with taking them because you might not know the other ways to do things by now. But if you're not using those methods from Wednesday's lecture to work with your data effectively, you might get jammed up on this one. That's why this is the next lecture task. Right? Yeah, and in the second part of lecture task 1, you can get through lecture task 1 pretty easily. The first method in lecture task 1 pretty easily with a lot of different approaches. But to do the second one, it's a bit tougher, and to do this one, things are just a little bit different. So that's your next task, standard deviation. So let's talk about our lecture content today. Let's get into this. Let me scan chat quick. Hi. So let's talk very briefly about runtime analysis. I don't want to steal too much thunder away from CSE 250. CSE 250, you are going to dive deep into runtime analysis for the entire semester. You'll learn a lot about it in 250. I just want to give you a brief overview, just to give you a little bit of foreshadow for next semester of what you're going to be doing, and it's going to be a lot about efficiency. In 115 and 116, we're showing you like how to get things done. And in 116, we start to focus on how things work in the machine. How is memory managed? How does your program execute? How are types stored and created? Things like that. And then for a lot of the rest of your computer science and engineering curriculum, it's going to be a focus on efficiency and doing like more specialized things in specialized courses. But in 250, we really start that talk about efficiency. We don't really care too much in 116 about efficiency, but I want to talk a little bit about it when we're talking about these topics. So runtime analysis, we usually measure things asymptotically using big O notation. The very short TLDR of big O notation is it's a measure of the order of growth, and we ignore all constants. So if we say like something is an n squared algorithm, that means as the input grows, the runtime is roughly growing by the size of that input squared. And we measure this in terms of like steps that an algorithm takes, of number of basic operations that are computed throughout the runtime of the algorithm, which can be any like basic operation, plus, minus, potentially division and multiplication, logical operators, things like that. How many of those do we take? And then what's the rate of growth as the input grows? We measure the input usually as a lowercase n. For most purposes, especially in 250, n is going to be the size of the input data structure. So for today's lecture, we're going to be sorting lists. N is the number of elements in that list. How long does it take to sort a list of n elements? And we want to measure that asymptotically. So if we have a runtime of big O of n, that means that the runtime grows linearly with the size of the input. So we have some function, some linear function for our runtime that could be, and we ignore all constants, so it could be like 1,000,000 times the size of the list. Could be our actual number of steps taken to run that algorithm, but we still call that linear. We still call that big O of n. We ignore all the constants and just focus on the asymptotic growth of that runtime. So that's how we measure things. For better or worse, we ignore all constants. When the numbers get really big, the constants tend to not really matter anymore anyway, unless they're just absolutely astronomical constants. So we usually get away with that in computer science pretty well. So let's do a quick runtime analysis of our selection sort that we saw last lecture. And I misspoke last lecture. I thought I had a selection sort method in the repo that didn't use var, and I went to look and I don't. For merge sort, I wrote one. The harder one, I wrote one. I tried to write one real quick before lecture, and I just ran out of time. So maybe tonight I'll go and write that. But especially if anyone's curious, just prod me a little, and it'll motivate me to actually write it. But without that, I don't know if anybody's waiting for that. So, but here's our selection sort that uses var. I have one loop that runs n times. This runs exactly n times, the loop that's iterating over each index of the input list. There are n indices because n is the number of elements in the list. So this loop runs n times. I'll say big O of n, but it's exactly n times happens to be in this case. Exactly n times this loop is going to execute. So we look at how much work is done inside the loop. We have some, I'll hold off that conversation, some operations though. But the big one that's going to increase our asymptotic runtime is this inner loop. So we have a loop inside of a loop. In most cases, most scenarios, this is going to blow up our runtime by quite a bit. So we have a loop in a loop, and here's where we're measuring worst case. In asymptotics, we always look at the absolute worst case that can happen. In worst case, this loop is going to iterate n times, or n minus 1 times, I guess. So we're going to have an O of n number of iterations of this loop. So if we have O of n iterations of this loop, and each time this loop iterates, it's going to iterate n times here in the worst case, well, we have a total runtime of n squared for the entire algorithm. And this little guy right here is actually really nasty. This apply method in a list, this is actually an O of n operation. This is, I very briefly mentioned in last lecture, like my implementation is actually really bad. That makes this O of n cubed. So this is a very slow runtime method. Apply on a list, or if you remove the word apply and just do parentheses to access an element, that's an O of n operation. That's a very slow operation. And in fact, appending to the end of a list also, very, very slow operation. but they're both O of n operations. So even though selection sort is an n squared algorithm, my implementation of the algorithm is n cubed because I'm being sloppy with my use of data structures. It's something that's very important, especially later on in your careers in 250 and 331 when you take those courses, and out there in the real world, of course. Even though you have an algorithm that you've proven is a certain runtime, if you have a very sloppy implementation, like I do here, intentionally, of course, like I do here, you're going to get even worse than that optimal runtime. I'm going to also show you a sloppy implementation of merge sort, which is going to end up turning merge sort into an n squared log n algorithm, which obviously defeats the purpose of even running merge sort. I could just clean up my selection sort and have an n squared instead of going to merge sort and getting something even slower. So that proof is a little bit hand wavy for those of you who want to see a little bit more of the math. So that inner loop doesn't always run n times. We just said it's O of n because that's the worst case. But if we analyze this, if we break this down, each time we run that inner loop, the first time we're looking at every single index in the list, every single one of them. The next time we have the value at index 0 locked in, and then we're going to look at the next n minus 1 elements and compare all of them, then the next n minus 2, so on and so forth until we start getting down to 2 and 1, get down to the end of the list. If we sum this up, this should look familiar. This is going to be n squared over 2 plus n squared, or n times n plus 1 over 2. I wanted to break it into its terms. And then we look at the highest order term and ignore the constants and say that that's O of n squared. So if you don't like my hand wavy, well, in worst case, it's n squared, or n iterations of that inner loop. But actually, it's, sometimes it's only one iteration. Sometimes it's a lot slower. Here's a little more mathematical proof of that one. Even when you sum up the total iterations of both loops combined, considering them both simultaneously, you're still going to get an n squared term. It's n squared over 2, but 1/2, that's a constant, and we don't care about it, especially a constant of 1/2. That's not going to affect things too much. In the real world, yeah, if you can get a ×2 increase in optimization of your program, definitely go for it. When we're measuring asymptotics of algorithms, we're usually not that concerned. This is the same as if it was n squared times 2, we would treat those the same. Even though there's a 4x factor, we don't care when it comes to asymptotics, when we're doing asymptotic analysis. Because both of those, n squared over 2 versus n squared times 2, both of those are extremely better than n cubed. And they're both way, way worse than n log n. So we don't really care about the constants too much. We're talking about orders of magnitude. Where does this thing even compete? So that's your very quick runtime analysis. You probably saw something about as brief in 115, but don't worry, in 250 they're going to hit you hard with the runtime analysis, with the asymptotic notation and the big O's. So in 115, you also briefly saw a merge sort. And when we teased this and we said it's n log n runtime, and we flashed the algorithm on the screen and said, wasn't that cool, and then moved on. We're going to analyze it a little bit more in depth this time and talk about what this algorithm is doing. With our goal today of bringing in merge sort is to show you how a recursive algorithm works with one example of merge sort, and with the intent of getting you able to write recursive algorithms. That's what today and Monday's lecture is all about, is getting you to the point where you can write recursive algorithms. Now, I don't expect you to be at that point at the end of this lecture, but at the end of Monday's lecture, that's where we're going to start decomposing some problems. If you had this problem and had to write a recursive method to solve it, how would you end up doing that? We'll get you a little bit of the way there today. But let's just see our first recursive algorithm, merge sort, and talk about how the recursive part of this works. So the algorithm itself on a slide looks pretty simple. If the input of merge sort has just one element, return it. If you have a list of one element and somebody asks you to sort it, just shove it back in their face. Say, it's already sorted. It's one element. I don't have to do anything. There's nothing you have to do to sort that thing. It's already sorted. If there's more than one element, we're going to split the list in 2 halves. We're going to recursively call our algorithm on each half. And then whatever we get returned from our algorithm itself, we're going to merge those 2 sorted lists together. And that's merge sort in a very small nutshell. We have to, of course, have to spend most of today's lecture unpacking all the details here. But this is the big trick that we want to talk about, this recursive call. So first, let's solidify what we mean by merge sort, what we mean on that previous slide. So say we're given this input, we're given the task to sort this list. We're going to look at this list, and our algorithm is going to say, is this list length 1? No. So we're going to split this in 2 lists. We're going to split it in half as evenly as possible. Of course, I have, the size of my list is a power of 2 to make it nice and pretty on the slide. But if it's not a power of 2, your code will just have some way of saying this side gets the extra element. So I'm going to split this in 2. And for each of these, I put another frame on the stack, another call of merge sort, and I say, is this of length 1? No, it's not of length 1. So we're going to split it in half again. We're going to get 4 more calls of merge sort, and for each one of those, we're going to say, is this length 1? No. So we're going to split those again until we have 8 calls to merge sort that are going to end up on the stack, all of length just 1. Now merge sort knows what to do. It says, this is a list of length 1, I'm just going to return it. You give me the list with just the element 51, I'm just going to return it. It's already sorted, it's only 1 element. No work to be done. Where the real sorting happens is on the merge side. So we have these 8 calls, they're all going to return, they're just going to return the lists that were given. And we have the task of merging these lists together. So we have 51 and 1, these 2 lists, and we're going to merge those into a single sorted list. So we're going to say, well, 1 comes before 51, so put 1 in front. Merge these 2 together, 19 comes before 100, 2 comes before 8, 3 comes before 4, and merge those already sorted lists. And it's important that the lists are already sorted. So then we have these 2 lists, we have the task to merge. And we're going to merge 1, 19, 51, 100, 2, 3, 4, 8. And then we have these 2 lists, we'll merge these and get our final output. So at a very high level, this is what merge sort is going to do. Yes?
What do you do if your input list has an odd number of values?
So if it's an odd number, you split them as evenly as you can, and either the left or right just gets an extra element. And when you get down to like the bottom call here and you have 3, one of them will just go to the base case with 1 element, the other will have 2, and then the 2 gets split into 2 singleton lists. And then we have the total merged output. All right, so let's look at this in code. How do we, that's the concept of merge sort. Let's look at the code and how would we actually get that done using some Scala. So here's the algorithm. Merge, we're going to define later. This is a method that we're going to write, but I'm going to save the details for that for a future slide and a few slides from now. And let's look at the whole algorithm, because this is where like all the tricks happen. This is where all the magic happens. So if the data is length 1 or less than 2, just in case I end up getting a list of size 0, if somebody gives me the empty lists and asks me to sort it, I don't want my algorithm to break. So I'm just going to say if the input size is less than 2, just return that list. It's either empty list or a list with 1 element. Either way, it's already sorted. I don't got to do anything. Else, we're going to find the midpoint. And here I'm intentionally using integer division. So far when I talked about integer division, I always say it is a bad thing. Now I'm using integer division intentionally for its intended purpose. I'm going to take the length, divide it by 2, and ignore any remainder. So if the length of the input list happens to be odd, I'm effectively just rounding down. I'm taking the floor of that and giving the extra element to the right side of this split. Then I'm going to use this handy split at method, which is going to take a list and split it at a certain index and give me 2 lists that are going to be the left and right sides of that list. And then make the recursive calls. And via magic, it's going to work. So the recursive calls, we're going to call merge sort. Why can't I get anything highlighted the way I want to? these things. But we're going to call merge sort, which is the method that we're currently writing. This is recursion. When a method or a function calls itself, that's recursion. So we have calls to merge sort inside the definition of merge sort. And this is one of them topics that gets really mind-boggling when you start thinking about what the hell that really means. And we're going to take 2 lectures here to really think about that and let it settle in. It's one of those topics with recursion. I don't know what it is with this topic, but it's one of them topics that just doesn't make sense. And then you think about it for a while, and then it doesn't make sense. Then you think about it for a while, and it doesn't make sense. Then it still doesn't make sense. And then one day it just clicks. It's like, that's what recursion is. I get it now. And then you just understand recursion after that. It can be a tough journey getting to that point, but once you get to that point, I don't know. I've talked to a lot of people about this. They just hit that one point where it's like, I get it now. I get it. I get recursion. So if it takes you a while to understand really what's going on with recursion, it's perfectly fine. I did not understand it in 116. I'll be upfront with you on that one. It took me a few classes down the road. Like I stumbled through it in 116, and a few classes down the road, I think it was 331. When I finally got there, it finally clicked. Like it finally gave me that intuition. Like that's what recursion is doing. So don't fret if it takes a while to really get this. But we're going to have merge sort call itself. And by the way, merge sort is going to follow the same structure as our selection sort. Same exact thing. We're going to take a type parameter. We're going to take a list of that type. We're going to take a comparator of that type, and we're going to return a sorted list of that type. Okay, let's briefly analyze the runtime of merge sort. We'll get to the rest of the details and get to that merge, but I want to talk about the runtime first. In a sufficiently brief way, just like we did with the other one. These aren't full runtime proofs, by the way. You'll learn about full runtime proofs again in a future course. So, but let me do my really hand-wavy, like, this is kind of how the runtime analysis goes. So at each level of the recursion, when we visualize it from my previous slide, like we visualize the recursion going down like this, I'm going to call each one of these levels level 0, level 1, level 2, level 3. And I'm going to label those levels I, and I'm going to notice that for each level, I have 2 to the I lists of size n over 2 to the I. So when I is 0, I have 1 list of size n. When I is 1 on that second level, I have 2 lists of size n over 2. Then I have 4 lists of size n over 4, 8 lists of size n over 8, and so on and so forth as I go down that recursion. And my question is, for any arbitrary n, at what point does the recursion end? Well, I can answer that by answering this question, by solving this equation. It's when n over 2 to the I is equal to 1. That's when all my lists reach their base case. And depending on odd and even numbers, this could be off by 1. But again, 1, we don't care about 1. That's a constant. Asymptotically, we don't care. So roughly, this is going to be when we reach the base case, and we can solve for I and say I is log n. So we're going to have log n levels of that recursion, which means if we start with, say, 1,000,000 elements, by the time we get to the 20th level, we're going to be at our base case. Log n is a really powerful, logarithms are really, really powerful things in computer science, and anywhere else, but we love our logs in computer science. And notice that this log is base 2, but again, it's just a constant. We can factor that out as a constant, so we don't care. So in asymptotics, any log base is treated equivalently. We just call them all logs. We don't care about the base because we can just use our properties of logs and change to any other base by multiplying by a constant. So we don't care about the base, but technically it's base 2. So we have log n levels to our recursion, and we have to ask ourselves how much work we're doing per level. So per level, the work that we have to do is going to be merging a total of n elements across all our lists. We might have a lot of lists. We could have up to n over 2 lists. but our total work that we have to do is to merge n elements. So if across all our calls of merge, we're doing a total of O of n work, which means any individual call to merge is doing O of n work, then we'll have O of n work per level times log n levels gives us our O of n log n runtime that we're looking for. So so it's not a full runtime analysis, but it's showing that if we can run merge in linear time, we're going to hit our n log n. So our task becomes clear. We need to merge in linear time. We need to merge fast. We need to merge as fast as possible. You can't do sublinear time because you can't even read all the elements in sublinear time. So we need to merge as fast as we asymptotically can, which is O of n. That's our goal. All recursive functions should have O of 0 runtime. What does that even mean?
I think that's O of O runtime.
O of O? Oh, okay, that makes more sense. O of O runtime. That's a good one. I saw it was O of O too. I'm like, oh, they must have meant O of 0. There was a whoosh moment for me. So our goal is to merge two sorted lists in O of n time, and luckily we know how to do that. So to merge two sorted lists in O of n time, it's very important that they're already sorted. Both lists have to already be sorted. If they're not already sorted, our task is to take two lists, sort them, and then merge them. Well, at that point, if we can sort in linear time, we would have just done that from our initial list and not bother splitting it in two. So it's very important that they're already sorted. So we take two sorted lists, and we create two pointers that point to the first element in each list, and we're going to compare those two elements. Whichever one comes first, we're going to copy that one into an output list and advance that pointer. And then we're going to continuously compare the two values that are currently being pointed at and take whichever one comes first, copy it to the output, and then advance that pointer. Do that until we get to the end of one of the lists, and then copy everything from the other one over. So that's our merge algorithm that's going to get us O of n merging of two sorted lists. Visually, it looks like this. Say our task is to merge these two lists. We're going to create pointers, point to the first element of each list, and compare them. We're calling our comparator and comparing 1 and 2. And notice this is the only time our comparator comes into play at all. In the merge sort algorithm itself, we didn't care about it. We just passed it on to the merge algorithm. And merge cares about the comparator. Merge will call it. So we compare these two. 1 is going to come before 2, assuming we're sorting using the less than comparator. 1 is going to come before 2. So we copy 1 to the output, where we're going to actually output to the user, to the caller, and then advance this pointer. Compare 19 and 2. 2 comes first, copy 2, advance the pointer. 19 and 3, 3 comes first, copy 3, advance the pointer. 19 and 4, 4 comes first, copy 4, advance the pointer. 8 comes before 19, copy 8, advance the pointer. Now we've reached the end of one of the lists. Once we reach the end of one of the lists, we can just copy everything left in the other list. Just throw it all into the output. And we successfully merged these two lists in linear time. Every time we did a constant amount of work, we did one comparison, copied one value to the output list, and advanced one pointer. So we did 3 operations, constant work. And every time we do that constant amount of work, we got one more element processed and into the output list. So if we're doing a constant amount of work, and each time we do constant amount of work, we copy one element. To copy n elements, it's n times that constant, O of n runtime. Any questions so far? Might be going a little, I don't know if I'm going fast. I don't think I'm going slow, but I might be going fast. So we got our O of n runtime, which means we get our n log n runtime here. Nice for Solana. at the end of the first list, if there was, you didn't have to delete it. If there was a number lower than 19, 51, and 100 at the end of the first list, it wouldn't be at the end. So we have the requirement that the input lists have to be sorted. So if there was a number less than 19, 51, and 100, it would have to be up here. It would have to be, come before that 19, because these input lists have to be sorted. If there was a value less than these three at the end here, everything's going to break because we violated the assumption of merge. Merge is going to assume that the input lists are already sorted. If that assumption is not met, merge will not work. There will not be a way to get O of n runtime of merging two unsorted lists. Because there's a famous proof where using comparison sort, you cannot sort in faster than n log n time. It is not physically possible. It's not possible to do. There are proofs proving that it is literally impossible using comparison sort. So when you see a sorting algorithm that's O of n time later down the road and you come yelling at me, did it use a comparator? If it didn't use a comparator to compare two elements, it wasn't comparison sort and you can get faster runtime. But comparison sort can't do better than n log n. So if we have two unsorted lists that we have to merge, we effectively have the task of sorting them. We could just throw all the elements in one list and then sort that list. It has to take us at least n log n time based on that proof. So if these input lists are not sorted, we cannot merge in linear time. Unless, potentially there's some other constraints that we put on the input lists where we're not fully sorting. But if they're just arbitrary lists of elements that we have to merge, it has to be n log n. What we would do is combine them, just merge them, and then sort them. So if we're sorting in the middle of our sorting algorithm, then what are we doing? Because whatever we did to merge here, we would just make that our top level algorithm. We would replace merge sort with however we're sorting in there. So these have to be sorted inputs. Absolutely have to be. Yeah, you can bucket sort in O of n, but it's not comparison sort. The buckets themselves are not sorted. If you have a question, I really like this question, 331. You have a binary sequence, just ones and zeros, and you need to sort them. How do you sort them as optimally as possible? You can actually do that in linear time. You just scan through all the values and count the number of zeros. Then you write that many zeros, and then you write n minus that number of ones. So you don't actually have to sort them all. You just do one pass, count them, and then write everything. It's O of n. But you didn't ever use a comparator. It wasn't comparison sort. All right, let's move on. So let's take a look at merge. What we just saw in the slides, let's see this in code. And merge is going to take two lists of type T, our comparator, and return a single list with all those values concatenated, merged together. So for this, I'm going to initialize my pointers. I'm going to initialize my output list where I'm going to copy all the values. I'm going to iterate as long as I haven't reached the end of one of these two lists. So if my pointer is at the end of either the left or right list, I'm done with this loop. I'm going to use my comparator and say, whatever's being pointed at in the left list by the left pointer, does that come strictly before what's being pointed at in the right list by the right pointer? If it is, add from the left list whatever's being pointed at to my output list and increment my left pointer by one. Else, I'm going to give ties to the right side. So if it's identical elements, I'm going to say take it from the right side. Those ties can be broken arbitrarily here. And I'm going to say take whatever the right pointer is pointing at, add it to my output, and increment the right pointer by one. Once I'm done with that loop, I know I either hit the end of the right list or the end of the left list. I don't know which one. So I'm going to check. If we're not at the end of the left list, copy everything from the left list over. If we're not at the end of the right list, copy everything from the right list over to the output. Then finally return my sorted list. So nothing overly complex. It's coding up what we visualized in the previous slides. But this is very slow. I use that ugly apply. Apply is a very slow method when dealing with lists. And I also used append just to make sure this was a terrible runtime algorithm. We also used append. So all of these are O of n operations inside of merge. So our merge ended up being O of n squared, which makes our entire algorithm O of n squared times log n. Which actually, I believe, ends up flattening out to just log of n squared. But at any rate, we didn't get the efficient algorithm that we wanted out of this. The theory is all there. That's what we're concerned about. But in implementation, we didn't get there. I also use var all the time. But Jesse, you banned var in our homework. Why are you showing var in our lecture examples? All right. So here's an optimal one. This is getting n log n and not using var. It's going to be a little tougher to read, but you can see what I mean, what I mentioned in last class. When we embrace functional programming, our code gets a lot more expressive. I can say a lot more with a lot fewer lines of code. With our previous example, I developed the entire slide, setting up my loops and everything. Once we embrace functional programming, we're doing a lot of work here. So let me walk through this. This is going to be our second example of recursion. So I want to do the same thing that we did in the previous slide, merge left and right list of t using a comparator and then return that list. And I want to set this up recursively, and you're going to face this in your homework, where you want to write a recursive method that has a specific method signature that the homework assignment says, write a method that takes these inputs and returns this output. And you're going to be like, I really need an extra parameter to be able to get the job done. I'm faced with the same situation here. Merge sort is already defined. It's already calling a method that has two lists and says sort these, merge these based on the comparator. But what I really need is another parameter, and I'll talk about why in a second, but I want this extra parameter to be able to get the job done. So what I'm going to do is write the method the way that I want to, and then the method that's required, all I'm going to do is defer to the method with the parameters that I want, and then give some initial parameter, some initial value to that parameter that I added. This is a very common strategy in recursion. I want more parameters because parameters are the only way we can really communicate across recursive calls, is through parameters and return values. This is the only way across our recursive calls we can communicate. So I'm going to call the one with the parameters I want and initialize that value. So we have our public-facing recursive method. This is the one other people are going to call. And then we have our private recursive method, which is the one that's actually doing the work. And then the public one just defers to the private one with any initialization that we need. So inside this, what I want is the accumulator variable containing the output list where I'm collecting all the values. That's the accumulator's goal. Just like the accumulator in the accumulator pattern from 115, that's where I'm collecting all the results. Now I'm going to have that as a parameter, so each time I go through this algorithm, I'm going to add to this accumulator, I'm going to append to it, and pass it on to the next recursive call. So the next recursive call is going to get something extra in that accumulator, and then eventually when we get down to the base case, that accumulator should have everything that we need. And then the base case is just going to return the accumulator, all the finished list, and then everything is just going to return it back up the recursion and say, here's your finished result, and then return that to the public-facing method, and then return it to the user. So here we have two base cases. I'm going to look at the left and right list. If the left list is empty, I'm going to take everything in the right list and add it to my accumulator. This triple colon, so we use double colon to append one element, prepend one element to a list. Triple colon is going to take two lists and smash them together. So if you got two lists and you want all those elements to be in one list, triple colon gets the job done real quick. And I'm actually going to build my accumulator backwards, so when I hit my base case, I'm going to reverse it, and then add all the elements from the list that I need to it. Same thing if the right list is empty, smash the left list into that accumulator, but in reverse order. If neither of those lists are empty, I'm going to use my comparator, and if the left list should be added to the output, I'm going to add the first element of the left list to the output. Backwards, I'm going to prepend it, so I'm building the accumulator backwards. That's specifically so I can use prepend instead of append. We're going to see in Learning Objective 4 why that's so important. Appending to a list is very slow. Prepending to a list is very fast for very specific reasons. And then I'm going to call this drop 1 on the left list, which is going to remove the first element from that list. It's going to delete that first element and return the rest of the list. So I'm always only comparing the heads of the list, and then when I'm done with that one, I'm going to remove that element from the list to be able to effectively advance the pointer, but through recursion and neat functional programming tricks. Then the other list is untouched in the comparator for that. If I'm taken from the right list, same thing, but replace left with right and right with left, and make the recursive calls. And the merge sort algorithm itself, is it on the next slide? The merge sort algorithm itself didn't use any vars, so we don't have to modify that one at all. It was only in merge where we used vars, and we cleaned all that up by using some functional programming magic. I shouldn't say magic, but some functional programming techniques. Why is prepending faster than appending? Ooh, that's a good question. I mean, we're going to spend a lot of time in LO4. I'll try to give you a TLDR. Is there a good TLDR on this one? So a list is stored by pointing to the first element of the list, and then each element of the list points to the has a reference to the next element of the list. So to get to the end of a list, we have to go to the first element of the list, follow its reference to the next element, follow its reference to the next element, and then keep going through memory till you get to the end of the list. So if you're appending, you have to go through the entire list and then append to the end of the list. But if we're prepending and we have a reference to the first element of the list, well, we're just going to create a new first element and have that element point to the old first element, and then update our reference to point to this, to refer. I keep saying the word point. I intentionally try not to say that word at all, because pointers are a whole different thing. But a reference to the new head of the list, and then I don't have to touch anything else in the list. So that's why prepending is faster. Yeah. It takes two lists and combines them and returns a single list. So the triple colon, I have two lists here. Yep. So all my values will be this entire list, and then this whole list will be after that first list. So when we write recursive methods, did I even define base case? I use that term a bit. I guess this is the slide I want to define it on. So writing a recursive method, these are the steps that I recommend for writing a recursive method, is assume that all of your recursive calls are going to be correct. So if it's a recursive method, at some point in this method, you're going to call the method itself. Assume that all those calls are just going to return the correct values. And if you follow all these steps and set up your algorithm just right, then that assumption will be true by the magic of recursion. It'll just be true. That's really where the power comes from. And it takes some deep understanding of recursion to really see why that's going to be true. If you don't have that deep grasp, which I don't expect you really have yet, just assume your recursive calls will be correct, that they're going to return the correct values. So when we call merge sort recursively, we're just going to assume that's returning a sorted list. We're going to assume that we have those two sorted lists and then throw them in merge with the assumption that, okay, merge has its assumption satisfied because merge is expecting two sorted lists. We're going to assume that merge sort did return sorted lists, give them to merge, and then everything's going to work out the way we expect. So we're going to assume that that's correct and write all of our logic based on this assumption. Just don't even worry about your recursive calls. Like when you're in a jam and you're like, I don't know how I'm going to sort these things, but my task is to sort them. Make the recursive call and expect the recursive call to return the right value, and then just move on with the rest of the logic. Assuming that you have the power to make recursive calls that are going to be correct, build all of your logic around that, and design your algorithm around that idea that the recursive calls will be correct. Add a base case that has some trivial input-output behavior, something that you just can't get wrong. In merge sort, it was a list of size 1 or a list of size 0, an empty list. If you give me a list of size 1, you can't go wrong. You just return that list. That's our base case, something that's trivial input-output behavior that's just really easy to just straight up compute and get the answer. And then finally, making sure every recursive call gets you closer to that base case. If every recursive call you make gets you closer to the base case, you're eventually going to reach the base case. And when you reach the base case, what that returns is trivially correct, right? So when you reach the base case, this assumption, it's obviously correct because it's the base case. It's the empty list. It's a list of size 1. It's the input of 0. It's an input of 1. It's an empty string input. You're going to get the right answer because you hard-coded the right answer to solve that very trivial input. So this assumption is correct when you reach the base case. And then as long as all of your logic is correct, when you make another return that's not the base case, if all your logic is correct, then that will also return the correct answer. And whatever that returns the answer to, another call of this recursive algorithm, recursive method, well, that's going to get the correct answer, so its assumption is correct, and if its logic is sound, it will also return the correct answer. And we go all the way up the recursion, all the way up the return values, return all those stack frames, and eventually get the correct answer to our original input. Yeah?
So like the first example where so we have like a flag or whatever, base case of that was if like if the length of the string is less than 2,
Mm-hmm.
right? So we keep like recursively calling, splitting the list till the length is 2, and then it stops.
Yeah, and then we start returning. So as we're going down the recursion, as we're making more and more recursive calls, we're just throwing more and more frames on the stack. Once we get to the base case, that's when we're finally returning. Stack frames are returning to the previous stack frames. But nothing, everything's just getting more and more questions until we get to the base case, and then we start returning answers back up the stack frame. So for our merge sort, we assume our recursive calls are correct and write our method based on this assumption. So if our recursive calls are correct for merge sort, we can kind of build our logic. And of course, we're thinking ahead a bit to this one, making sure our recursive calls are getting closer to some base case. But we're going to build our logic based on the fact that these will return the correct values. So if I give merge sort the left list and the right list, I'm going to assume that it's going to return those lists sorted. And then merge relies on that assumption and returns the merged sorted list. I'm going to add a base case. If you give me an input of length less than 2, I'm just going to return it. And then I'm going to make sure my recursive calls always get closer to the base case. If we never reach the base case, we're going to have a bad time on that one. So each time I recursively call merge sort, it's with a list that's half the size of the input list. So if I keep dividing this list in half, I'm going to eventually reach this base case of size 1. And once all those 4 ingredients are mixed together, the algorithm just works. When you're writing your, I made all these points. Just one more point I want to make. If you don't ever reach that base case, you're going to have that infinite recursion, and that's where we're going to hit that stack overflow. We put too many frames on the stack. We just put an infinite number of frames on the stack until the program goes, that's too many frames, and just blows up. That's our stack overflow error. So when you see stack overflow errors when you're writing recursive calls, make sure you're getting to that base case because you're probably not at that point. All right, have a great weekend. See everyone Monday.